A long-forgotten Soviet spacecraft finally returns to Earth. This week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. On May 10th, Kosmos 482, a Soviet-era spacecraft that was originally designed to land on Venus, mysteriously plunged back to Earth after more than 5 decades in orbit, leaving experts scrambling to determine where it landed. I spoke with Ben Fernando, seismologist and planetary scientist from Johns Hopkins University. He'll help us unravel the mystery of Kosmos 482's fall, why we don't know exactly where it landed, and how new technologies are allowing us to better track these events. Then Bruce Betts, our chief scientist, joins me for What's Up and a look at other large human-made objects that have fallen back to Earth. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. The Venera program was one of the Soviet Union's most ambitious space exploration projects. It was designed to unlock the mysteries of Venus. And to this day, our only close-up images of the surface of that world come from those spacecraft. Kosmos 482 was meant to be a part of that storied mission. It launched in March of 1972. Its lander was engineered to endure the surface conditions on Venus. That includes hellish temperatures and crushing atmospheric pressure. But unlike its sister spacecraft, Venera 8, which successfully landed and transmitted data back to Earth, Kosmos 482 never made it out of Earth's orbit. A malfunction during its launch left it stranded, circling our planet for over half a century. Despite its long stay in space, Kosmos 482 was not just another piece of floating debris. This thing was built to survive Venus. Its reinforced body endured 53 years in orbit, while slowly descending inch by inch, until finally, on May 10th of this year, which was just the Saturday past, it plunged back to Earth. But even with all of our technology and careful monitoring, we aren't really sure where it came down. Its final moments were tracked by various international agencies, but we're still trying to figure out its exact landing location. One might ask, how do you lose track of an object that large? And what does that say about our ability to monitor the thousands of satellites and all those pieces of space debris that are orbiting above our heads? To answer those questions, our guest this week is Dr. Ben Fernando. We spoke just days after that spacecraft's fiery return. You may remember Ben from our conversation in our December 2023 episode called The Mystery of the Largest Marsquake Ever Recorded. Ben is a seismologist, a planetary scientist, and a postdoctoral fellow in the Department of Earth and Planetary Sciences at Johns Hopkins University. He studies seismic waves on Earth, the Moon, and Mars to give us a better understanding of planetary environments and their interiors. He's part of the science teams for NASA's InSight, Dragonfly, and Viper missions, and he's been studying how we can use seismology to track falling space debris like Kosmos 482. Hey, Ben, thanks for joining me.
Thanks for having me.
I'm really glad that we're getting a chance to talk about this in this moment. This is a story that's been building for decades, strangely. What is Kosmos 482? What was its original mission?
So Cosmos 482 was one of a suite of probes that the then Soviet Union actually wanted to send to Venus. And as you can imagine, getting to Venus alone is pretty difficult. Surviving to the surface is even harder. And so part of Cosmos 482 consists of a descent package, which is basically a very thick heat shield and a parachute. And the idea was that that would actually be able to survive entry through the Venusian atmosphere and return measurements from within that atmosphere. And that's something that actually only the Soviet Union ever managed with their Venera spacecraft. So Cosmos 482 was part of that program. Unfortunately, for some reason, there was an issue with the rockets when they were leaving orbit, and Cosmos 482 never made it out of Earth orbit. And so that was back in the 70s. And Cosmos 482 basically just stayed in Earth orbit, going round and round and round for the better part of 50 or 60 years almost. And over time, the Earth's atmosphere, though it's very thin up there, exerts a little bit of drag on the spacecraft. And finally, this weekend, after all those decades in orbit, the amount of drag on the spacecraft was so great that it finally re-entered the atmosphere. And what we've been looking at is trying to figure out if anyone knows where it went, if we can use any of our new sort of seismic tracking techniques to figure out where it may have landed or crashed, I guess is probably a better word. So, like you say, kind of a decades old mystery that's finally come to a conclusion of where this spacecraft would end up.
And now the mystery is compounding because even though it did come in sometime we think on Saturday morning, we're not exactly sure where it landed. What did we last hear about its location before it went down?
Yeah, so very often you get a big spread of uncertainties in terms of where people think things will re-enter the atmosphere. And that's just simply a case of it's difficult to figure out exactly what orbit these things are on and couple that together with, exactly what the state of the atmosphere is. So we can tell, it'll be on its orbit and it'll be happily along there and it will re-enter somewhere along that orbital track. But it's really difficult to tell exactly where along that orbital track it will re-enter. So I've seen quite a lot of sort of conflicting reports. The last report I saw from Roscosmos, that's the Russian space agency, they were predicting a re-entry in the Indian Ocean. That would be sort of just west of Jakarta, the Indonesian capital. Other folks have suggested that, well, actually, we kind of may have got some kind of radar return over Germany. And the EUSST, I think at one point had a location that was over Europe. Other organizations have released locations that were out in the Pacific. So we really got sort of a huge spread along one and a bit orbits of possible re-entry locations.
When I brought this story up with a friend the other day, their first question was, well, how do we not know where it's going to land? I mean, that seems like quite a wide range of possibilities for where it could come down.
Yeah, it's actually really tough to track things once they're within the atmosphere. So stuff that's orbiting, you imagine the International Space Station, there's lots of ways that you can track that. You can track it by telescope. For things that aren't, as big, you can track them by radar. So you bounce radio waves off them and that tells you how they're moving. Over time, you can work out an orbit. Trouble is that once stuff starts really interacting with the atmosphere, and I mean, it's below 200, 150 kilometers, the atmosphere is really starting to drag on it, there becomes a huge amount of uncertainty in exactly where in the orbit it's going to fall. And that depends on the state of the atmosphere, which depends on solar activity, et cetera, et cetera. It can depend a little bit on high altitude winds as well, how far across that track it will land. So once it's in the atmosphere, it becomes really difficult to track. And that's kind of what we're seeing here, that we knew it was probably going to re-enter within a very narrow window, but it's moving so fast that even, say, 30 minutes of uncertainty corresponds to tens of thousands of kilometers when projected onto the ground.
How heavy is this object? Because I imagine that also matters when we're trying to account for winds and things like that.
Yeah, it's a few hundred kilos, so it will fall pretty ballistically. And it's got that heat shield on it, but that heat shield, once it's in the atmosphere, will start to decelerate it. And once you're actively decelerating, the effects of winds and other imbalances can have quite a substantial impact on the trajectory. The other thing to bear in mind is, of course, that although it's very heavy, if you're sort of 100 kilometers up and you're, let's say, 10,000 kilometers away, changing the angle that you're pointing towards me at by zero point 0.1 degrees makes a huge difference in the sort of perpendicular to the trajectory where you'll end up landing as well. So that's one of those reasons why as well, even if we kind of knew exactly where in its orbit it would fall, recovering it, for example, was always going to be incredibly difficult.
And we do think that it probably made it all the way to the ground. Is that because it was built essentially to survive Venus?
Yeah, the current thinking is that it probably made it all the way to the ground and or the ocean, as is more likely the case just statistically. It's got that heat shield, which, as you say, was designed to survive re-entry through the Venusian atmosphere, which is much thicker than Earth's. It also had a parachute system. Most of the analysis I've seen suggested the parachute system probably wasn't operational anymore. So that would have taken it from, the heat shield will slow it down to a few hundred meters per second, and the parachute would do the rest of the slowing down. So it doesn't look like it would have been a soft landing by any means, just because the parachute system probably wasn't working. But as you say, most predictions suggested that at least some fragments of the spacecraft would make it to the ground, and probably one quite large fragment of the main descent body.
Are people out there just like scouring the earth trying to find it? Or are we trying to figure out with science more where it could be located before we're making that effort?
I wouldn't be surprised if some folks have headed out to try and find things, but that's genuinely trying to find a needle in a haystack. Even if you imagine that you know its orbit very precisely, and you can tell sort of perpendicular to the orbit that it's plus or minus 10 kilometers away. If you take that 20-kilometer wide strip and you multiply it by the 10,000 kilometers of uncertainty that we have here, that's still a huge area that you would have to search. When something fragments, actually you end up with debris scattered over very large areas. So if you find one piece, it's probably easier to find others. This is more like rather than finding, a handful of rice chucked over the floor and you found one grain, you found it. This is like probably more like finding, I don't know, like a single loaf of bread. Like you've actually got to find that one thing. And of course, most of the Earth's surface is ocean. So statistically, in general, things tend to fall over the ocean. There's possible that this thing fell over land and someone might at some point find it. But even from the last orbits that were predicted, quite a large proportion of that time was over the Indian Ocean and then over the Pacific, where nothing would have been recovered if it did fall.
Well, the Venera program had several accidents along the way with several of its spacecraft going awry. What happened with this one, and where did it fall within the initial Venera program?
Yeah, so as you rightly say, Venera had a bunch of different issues with it. Most famously, one of my favorite ones is they tried to make some measurements of the Venusian surface, but they had like a little lens cap, something like that popped off the spacecraft when they were on Venus with one of the Veneras, and it kind of landed in the way of the sensor. So the sensor made some really good detailed measurements of the lens cap. Full credit to the engineers back then. It was it was a pretty tough game to play in the 1970s and 80s. But as you say, what happened with Cosmos, as far as we can tell, the Soviets basically put it into a parking orbit. So that means that it's a bit different to some missions today. They didn't just go straight from the Earth's surface up and then not really enter Earth's orbit, but just like shoot off to somewhere else. They put it into a parking orbit where it sat for quite a long time. And it sounds like after that happened, the engines sort of failed and they weren't able to sort of propel themselves off to Venus. Exactly what the details of the reason for that are, I'm not entirely sure if that's ever been released, but it basically meant that this thing ended up in a low Earth parking orbit for about 55 odd years, 1972 to 2025, I guess, and then eventually re-enter that atmosphere. So I guess it's just a sort of reminder that space has always been hard and space always will be hard.
And hey, even after all that, they still were the only nation to successfully land on Venus. So all
Exactly.
credit to the Soviet space program. That is still an absolutely amazing achievement. But this wasn't
Absolutely.
the entire spacecraft we're talking about re-entering. There was a whole other portion of the spacecraft that, landed much earlier. What happened with the other half of this thing?
Yeah, so part of the spacecraft, the main bus, the rocket stages, actually entered the Earth's atmosphere around 1972, maybe a couple of years later. So what that basically means is that those fell to Earth way back then, and I believe that some portions of the debris were actually found from that initial re-entry back in 1972, sort of the southern hemisphere around New Zealand. And it's believed that they came from the sort of main bus rocket portions of what is now Cosmos 482. I don't think that the Soviet Union ever really acknowledged the debris that was found in New Zealand was part of this spacecraft, so perhaps we'll never know for sure. But I think the analysis that was done on it suggested that it was Soviet in origin. Of course, now we've got much better technology to determine orbits, so we could figure out. There was a few folks, including at Harvard, who worked on this, figuring out exactly what orbit this object was in and what it might correspond to. And then they eventually figured out that that orbit was decaying and it would re-enter the atmosphere.
It's a shame that the Soviets didn't claim ownership of that because that means they didn't get their material back. Aren't there laws that say that if it's your nation that drops something and you say it's yours, then you could take it back and do all your testing and even put it in a museum?
Absolutely. That is, in theory, what the law of outer space requires you to do. In practice, especially in the 1970s, of course, proving, as it were, that something is someone else is challenging, something belongs to someone else is challenging. I believe scientists in New Zealand did sort of quite conclusively demonstrate this was Soviet technology based on the materials, the markings, etc. But the Soviet Union denied all knowledge of it, and as such, it's probably not worth a diplomatic effort to return it. That's, in some ways still the case today. That's what the law says. actually enforcing that, especially if it's not a government vehicle, can be really quite tricky.
Are there any other Venera spacecraft that ended up stuck around Earth that are still up there? Or I guess we have to call them Cosmos now because they didn't actually make it to Venus.
Yeah, there are a whole host of spacecraft that were meant to make it to some target or another at some point and didn't. And that's been the case since, the early days of the space program. One famous example that wasn't a Venera spacecraft, but did happen much more recently was in 2011. There was a Russian spacecraft called Phobos Grunt, which was meant to go to one of the moons of Mars. Very similar story. Ended up in a low Earth orbit, couldn't make it out of orbit, and eventually burnt up and disintegrated in the atmosphere. I don't think any debris from that event has ever been found. Again, over the ocean, most likely. But that's kind of a continuing story. Of course, there are many other objects that were never meant to make it into interplanetary space, which, when they're done in low Earth orbit, they're kind of boosted a little bit higher, but they will. Some of them eventually decay and re-enter the atmosphere as well. So in addition to the kind of past Venera era spacecraft that have done that, this is still something that happens with modern spacecraft when you end up in a parking orbit and then something goes a little bit wrong.
Yeah. And we'll talk later in the show about some of the largest objects that have come down to Earth. There have been entire space stations that have crashed down through the atmosphere. So this is not by any means the largest thing that's ever crashed down, but really interesting to know that we have to keep track of these over time because, especially if they're large enough and they are capable of hitting the ground, we want people to be safe. The likelihood that it's going to hit anyone's house versus the ocean, as you said, very, very small, but still good to be aware of.
Yes, absolutely. So, like many commentators have said, your likelihood of being hit by debris is much less than being, winning the lottery. But equally, we have re-entry events happening on a daily basis now. There's huge amounts of stuff coming into the atmosphere. So being aware of those risks, and then that involves sort of planning, monitoring, but then also responding to those risks because it's not just about being hit by something. Occasionally, things do re-enter the atmosphere. There was a very famous example in Canada from the Soviets, also in the 1970s, I believe. There's stuff that's sometimes quite nasty that re-enters the atmosphere. So famously, I believe it was Cosmos 954 re-entered the atmosphere over Canada in the 1970s. It actually had a nuclear reactor on board. So
Oh.
it scattered radioactive debris all over northern Canada, and there was a huge cleanup operation associated with that. Of course, we hope that won't happen anymore. The number of nuclear reactors left in orbit is small-ish. It's a few dozen from my understanding. But being aware of those risks and then responding to them when they do happen is really important.
Yeah, and this is a global effort. Do you think we're prepared to mitigate these kinds of risks as more and more objects come down?
Honestly, I really don't think we are. As we've seen from this event, in some ways, Cosmos 482 was quite small, but the fact that everyone lost it, at least the public releases, no one entirely sure where it fell, that's problematic in a way. And that's not because people haven't been trying hard or doing their jobs. It's because it's a really difficult problem. But at the moment, we just don't have the network of sensors around the world to fully capture the picture of re-entering space debris. And that becomes problematic because if you imagine if there was, say, radioactive material on board Cosmos 402, which there wasn't, thankfully, and that had to be recovered, it would be much more difficult if we couldn't figure out where it had ended up.
And this brings me around to your work because the last time we spoke, we weren't even talking about planet Earth. We were talking about Mars quakes. How
Mhm.
does your work in seismology connect to the story of this object falling down to Earth and our ability to track it?
So when we last spoke, and hope everyone's listened to the episode, if not, they should, we were talking about how impact events, predominantly on Mars, can be detected through seismology and why that's such a useful probe of the interior of the red planet. And the way that we detect those impact events, sometimes we record the waves from them actually hitting the surface. So, meteoroid comes in, explodes on the surface, creates crater, creates seismic waves. But what we also detect is what we call the air wave. So if you imagine that thing is coming in, it's creating a sonic boom, maybe it explodes in the atmosphere. Those all produce acoustic waves, which will propagate to our seismometer that we can detect. What I realized sort of a few months ago / a year ago is that a lot of these space debris events were creating sonic booms, which were probably detectable on the worldwide seismic network. And that wasn't necessarily a new idea. Folks had thought about sonic booms from space debris before. They thought about acoustic waves before. But the big difference here is that the seismic network around the world is much larger than the acoustic network, at least the open source seismic network. So we started looking at whether you could track space debris re-entering the atmosphere using seismology. And it turns out that you can. It's actually significantly easier in some ways than I thought it might be, so long as you have a re-entry over an area which has seismometers. And most places in the world that are inhabited have some seismometers nearby. The density varies wildly, but in general, most places have at least some seismometers nearby. And so as that space debris is producing a sonic boom as it re-enters the atmosphere, that sonic boom propagates down to the ground. You can track it across the seismic network exactly the same way that we sometimes track bolides, meteoroids burning up in the atmosphere, or indeed on Mars actually impacting the surface.
But if it lands in the ocean, then we're not going to be getting those seismic readings necessarily. In that case, would we then turn to waves in the ocean, or is it just a lost cause?
Really good question. And that's kind of a big question that we're working on at the moment. We do actually have a lot of seismic sensors in the ocean, but they're just much less dense than they are on land, and they often take very different forms. So when you say waves in the ocean, you're right. We're still looking at acoustic waves in the ocean. So they are not unrelated to seismic waves. We're not looking at, what you might call sort of inertial gravity wave. We're not looking at waves breaking on the surface of the ocean. What we're looking for is seismic/acoustic waves propagating in the ocean. And to record them, sometimes you'll pick up the signals on land, but you're right, in general, that's much harder. We have sensors called OBSs, ocean bottom seismometers, which sit on the ocean floor in some places. They record seismic signals. We have techniques these days called distributed acoustic sensing, which basically uses fiber optic communication cables or dedicated fiber optic cables to record vibrations, which we can associate to seismic/impact events. And then there's also sensors in the water column called hydrophones, which will actually detect vibrations in the water directly. Trouble is, there are far fewer of those, and also the ocean is a much larger place. So we can't just pull all the data from all of the ocean stations the same way we can pull all the data from all of the seismic stations and look at it in real time. What we can do, of course, is keep an eye out. But the trouble is that some of those sensors don't return their data in real time either. So if we did want to go hunting on the OBS record, in general, you have to wait until either one of the data modules or the entire sensor is returned to the surface. And as you can imagine, they're very expensive to deploy, so they don't bring them up that often.
Oh, wow. What is the usual purpose of these sensors, given that you have to go return them from the bottom of the ocean?
Yeah, so the OBSs specifically, their job is generally to study seismology associated with oceanic processes, which in general either means subduction, so that's an oceanic plate in general sliding below a continental plate, or rifting, so that's new oceanic crust being created at a mid-ocean ridge. There are other things that people have studied, but in general, big OBS deployments are often to study one of those two sets of processes. The other sensors, the fiber optic ones, the majority of undersea seismology that's been done so far, those are actually communication cables that we call dark fiber because they haven't been connected to the sort of global comms network yet. They're just kind of sitting there a bit redundantly, waiting until they're needed, simply because it's easier to deploy two at once than it would be to deploy one and then go back 10 years later and deploy another. Then, of course, there's a third set of dedicated hydrophone sensors. The civilian ones, at least, are a lot of them are operated by an organization called the Comprehensive Testband Treaty Organization. They have a network of, I think it's 11 around the world, or 11 stations with multiple sensors. And those attempt to detect any vibrations that might be associated with illicit nuclear tests underwater. So really in the ocean, when it comes to sensing seismic waves, there's a whole host of different instruments that we're trying to work with. And we think that when the space debris hits the ocean, especially if it's something big like a space station in a few years, it will probably make quite a loud bang. And it might not be obvious, but sound actually propagates really well through water. There's a reason that whales learn to sing, for example. So if stuff is hitting the water going that fast, we think it's quite likely that it will end up being picked up.
This was an uncontrolled reentry, but usually when there are large objects, say like the International Space Station or other things like that, we plan for where they're going to come down, and they usually come down near Point Nemo in the ocean, which is really, I mean, it's literally the furthest away from humans you can get, basically. Are there sensors out at that location for that purpose, or is that just too remote?
No, there aren't really any dedicated sensors that have been deployed to track space debris at this point. There are ocean bottom seismometers that are deployed out in the open Pacific occasionally, but as you say, that's such a huge, vast area of the South Pacific that the chances of being very close to one are small. So one thing we've been thinking about, is if this is going to be a designated graveyard for spacecraft for, I would guess, forever, right? Like that, I don't see that changing anytime soon. We're not going to swap to dumping them over Antarctica. Maybe it's an area that's worth thinking about having additional ocean-based or seafloor-based sensors, because it's all well and good tracking stuff from the atmosphere. We know that works. You can see space debris from orbit as it's re-entering, but that really doesn't tell you if it hit the surface or not. And you might say, well, at some level, it doesn't really matter because there's not a huge amount we could do about it. But still, it would be useful to know where this stuff is entering the ocean. And, if it doesn't end up at Point Nemo is good. The ocean is deep, stuff sinks to the bottom there. It's kind of inactive, or at least if it's having an effect on local biology, we won't know about it for a while. But there are plenty of other areas in the Pacific that are far more environmentally sensitive, where it would be really useful to know if stuff is actually falling out of the sky or not.
My understanding is that Point Nemo is actually kind of like a deoxygenated patch of ocean, essentially. It's not as biologically active as other locations, which is part of what they chose it for. They don't want to hurt wildlife, but you're right. These things could definitely hurt some wildlife out there if they're, not protected.
Yeah, I'm not a biologist, but I can very much imagine in 100 years a story coming along about how all the stuff at Point Nemo is sort of dead or contaminated with some kind of rocket motor byproducts or something like that, just because there is a huge amount of stuff re-entering the atmosphere these days, and that amount is only going to go up.
Well, that makes this kind of seismic tracking all the more important. Before, when we were talking about Mars, we were talking about the fact that you basically only have the InSight detector for seismology that allows you to kind of pinpoint the location of things. So it's hard to tell, say, the source of something like the largest Mars quake. You can try, but it's harder to triangulate. But on Earth, there's way more sensors. Do we have enough that if something this large comes down, it really does help us pinpoint its general location?
Yeah, so general location, yes. The case studies that I've kind of worked on, we have a reentry over Southern California, which we tested a lot of these techniques on. The great thing about Southern California, I guess, if you'd been based in LA, or just north of LA, like the Planetary Society, you would have seen this thing come over. It's one of the most densely seismically instrumented places in the world. So it's a really good place for working out if our techniques work. What we're then trying to work out is, how widely can we apply these techniques to areas that are less well instrumented? And it looks like we can do a pretty good job, actually. So we've been looking at reentry events. For example, there was one around Christmas time over sort of Louisiana, Arkansas, which we picked up, despite the seismic network in that part of the country being very sparse. We've also been looking at sort of uncontrolled reentry events from Starship over the Caribbean, which it looks like we picked up. So although the networks aren't as dense as they are in Southern California, once we've kind of figured out what we're looking for and how to process the data, we actually don't need that denser seismic network to start making measurements of the debris. And so a single seismic network, if it picks up that sonic boom encodes information about altitude, speed, fragment size, Mach number in actually a slightly decoupled way from speed as well. That's great. So with a single sonic boom, we can make some set of estimates. Obviously, the more that we have, the less that we have uncertainty on those results, that we're not sort of redundantly, we're not measuring multiple parameters at the same time. So we can pick things out. We can start to determine trajectories a little bit more accurately and speeds a bit more accurately. But we don't need that denser seismic network to do it. And so in some ways, it's a very powerful technique for what we would kind of call ground truthing. We know where we think it should re-enter. We have satellite measurements of it, maybe at the top of the atmosphere re-entering. Now we have ground truth that in theory will be sensitive to the entire propagation path. So the entire time that space debris is supersonic, it should be producing sounds that we hear.
That's really interesting. And I imagine that helps as well when you're trying to decouple that data from the rest of the data that are coming in on these seismometers.
Exactly. And so when I started this project, I was very skeptical that it would work. It was just kind of like, let's have a look, because I figured that trying to pick out a sonic boom in Southern California would be tough, right? Because Southern California is a pretty loud place, both in terms of people and earthquakes. But no, the signal was there. And, we have the advantage that it's going very fast, right? It's going about 8 kilometers per second. So that's about 5 miles per second. That's much faster than both, cars, trains, planes, and people, which is good. So we can tell the signal apart. But it's beautiful. We recorded it on about 150 stations across the state, possibly somewhere into Nevada as well. And so from that, it becomes easier to figure out how will these signals look different. And, just as a planetary society kind of reference, you'll know that most of LA is built on a giant sedimentary basin.
Mhm.
The way that sonic booms present themselves when you're over a sedimentary basin is quite different. So we see the signals looking quite different over kind of metro LA compared to when they're out over the Sierras, just because the geology is so different as well. So again, having this sort of test case that's really well instrumented with hundreds of stations allows us to understand, what exactly is the variation in waveforms that we're going to see. How can we be sure that we're really picking real sonic boom signals, et cetera, et cetera.
I love that you bring that up because living in California, we experience earthquakes so often that we're very familiar with the fact that depending on what ground you're standing on, that earthquake is going to present itself very differently.
Absolutely. And it's just the same. So, sort of sediment layers that are soft, unconsolidated, you'll often get energy going on for much, much longer. That makes it more difficult to pick a precise arrival time and a precise end time for the sonic boom. It's exactly the same with earthquakes. Those sediments are often sort of the most dangerous to be on because they end up with this long period sort of ringing of energy. And, in extreme cases, they can even sort of do what we call liquefaction, where they basically stop acting as a pure solid. Of course, here, the sonic boom is not dangerous. If you were close enough to it, it might break a window or, hurt your ears a little bit, but it's not going to bring down a building. But the physics is much the same of how it couples into the ground.
Yeah, that's always the advice I give to people whenever they're like, what do I do if I think there's a large thing coming in out of space? I'm like, step away from the windows. That's basically what we learned from Chelyabinsk and other locations. Just get away from the windows.
Absolutely. If you see something very bright and you think it might have exploded, probably turning away from it and turning away from the windows is the best that you can do. It's extremely unlikely that you'll actually be injured by the object itself. If you are injured, what we saw in Chelyabinsk is it's by things falling on you, by broken glass, by people getting distracted while driving, et cetera, et cetera. It's not that you're going to get hit by the space debris. That's very unlikely. What's much more likely is that people become distracted or injured by sort of secondary effects.
I know I would be.
Absolutely.
We'll be right back with the rest of my interview with Ben Fernando after this short break.
Greetings, Bill Nye here. The U.S. Congress approves NASA's annual budget, and with your support, we promote missions to space by keeping every member of Congress and their staff informed about the benefits of a robust space program. We want Congress to know that space exploration ensures our nation's goals in workforce technology, international relations, and space science. Unfortunately, important missions are being delayed, some indefinitely. That's where you come in. Join our mission as a space advocate by making a gift today. Right now, when you donate, your gift will be matched up to $75,000 thanks to a generous Planetary Society member. With your support, we can make sure every representative and senator in D.C. understands why NASA is a critical part of U.S. national policy. With the challenges NASA is facing, we need to make this investment today. So make your gift at planetary.org/takeaction. Thank you.
How many more sensors do you think we would have to cover the Earth in order to have a comprehensive understanding of how much stuff is actually hitting the planet? Because as you said, it is very difficult to track things just coming in out of space randomly. This might be the better way to do that kind of measurement.
Yeah, so one thing that we've been thinking about is rather than deploying individual seismometers, deploying these specific fiber optic cables that are designed to be seismometers rather than designed to be communication fibers. And they're not cheap, so we're not talking tens of dollars, but they're also cheaper than deploying a line of 1,000 seismometers. And the reason that these might be interesting is that we know they pick up sonic booms. They're not as sort of good, if you like, as traditional seismometers. They don't give you that three components of ground direction. They don't tell you the ground is moving this much this way, this much east, this much up. But they do give you some measurements of ground motion. They're what we call a distributed sensor. So you can have a fiber that's 50 kilometers long, and it's effectively like having seismometers along that 50 kilometers spaced every few meters. So for monitoring, it's really a really powerful technique, and it's something we've been working on analyzing data from space debris on distributed sensors. Of course, I'm still not at the point where I think, we should be running fiber optic cables around the entire continent. But as you say, there are areas which are clearly of greater concern than others. So, for example, planned re-entries of things that are delivering a payload back, they very often happen in the US over Nevada. In Australia, they happen over Woomera in South Australia. Those areas are on the order of, tens to hundreds of thousands of square miles. If you are interested in kind of instrumenting them, what about setting out some fibers, a little far enough away that the objects are still supersonic when they re-enter, but you can monitor, you can test. Of course, if you really are worried about particular areas, so Australia, just from the sort of odd coincidence of geography and where other countries launch from, they're very worried about debris falling over the Great Barrier Reef. They do get a lot of re-entry events over Australia, and that's a very environmentally sensitive area. What about thinking about putting out some distributed sensors there? And, I don't want to make it sound like space debris is as big a risk as, earthquakes in California right now. It clearly isn't, but it's a problem that keeps growing and will keep growing, I think, probably forever, or at least until we get a handle on the debris problem. So it's worth thinking about how do we instrument and monitor these events, these objects, given that at least at the moment, we're not doing it to the level where, it's been almost 48 hours since Cosmos 482 re-entered. No one's entirely sure where it went, or if they are, they haven't, release that publicly and help to generate a consensus. And I think that sort of having sensors which work towards that goal would be a really useful thing to do.
Especially considering that they could be used not just for this kind of space work, but in general, the more seismographs, seismometers we have around the world, the safer we are, and the earlier we can report things that people can get to safety during these kinds of large earthquakes and things like that.
Absolutely. One of the wonderful things about seismology is that you can use it for a whole host of phenomena. So as I mentioned, we have sensors out there which are designed for communication. They're not even meant to be seismometers. We have other sensors which are designed to detect nuclear tests. We have other sensors which are designed to study subduction processes, other ones which are designed to study coupling from the atmosphere to the ground. All of those things are things you can study with seismometers. And in general, the data is also made available online and open source, which is wonderful.
This just makes me think, though, that we need some kind of like space traffic control or something to figure out when and where these objects are coming down.
So that does sort of exist. The Joint Space Operations Center and Space Command in here. So JSPOC is a partnership of a few nations, the US, UK, Australia, Canada, New Zealand. They do track these things, but again, they're much more worried about stuff re-entering the atmosphere rather than where did it fall on the ground necessarily. So I'm sure that they're keen to know about it, but that's not necessarily their remit. Then, of course, many nations have their own domestic space agencies or sort of monitoring agencies which do look at these things. But I think one thing we've seen is that the coordination probably could be better. And a lot of those are sort of military or military adjacent organizations, whereas part of the response, of course, to Starship, for example, was clearly a civil response to debris being scattered all over islands in the Caribbean, which will require a degree of cooperation that did work, but perhaps could be made more efficient as well.
We've been talking mostly about how to use seismology in order to find these things, but you did mention earlier that we could be using more acoustic sensors around the world. How does that acoustic sensing network compare to the size of our, seismic sensors? And do you feel like we need more of them for this and other purposes?
So acoustic sensors are great. They're basically measuring the sound waves, the low frequency sound waves in the atmosphere directly. There are far fewer of them available open source around the world. The majority that people tend to use are operated by the Comprehensive Test Ban Treaty Organization, but there are other groups that run them. And the advantage there is you're not detecting the sonic boom once it's coupled into the ground, you're detecting the sonic boom in the atmosphere itself. So in some ways, it's a purer measurement, if you like. Whether that distinction is important or not can depend on exactly what you're trying to find. I would say that having more acoustic sensors would be great. In general, I think the level of sort of community knowledge about acoustic processes is probably smaller than compared to seismic processes, so it would require training people sort of in that data, which is quite different. But yeah, I think that acoustic sensors are certainly another possible option. I haven't seen sort of any specific proposals for space debris monitoring networks, but that acoustic network could probably be quite a powerful complement to people doing other kinds of atmospheric science for which the infrasound recordings would be helpful.
Well, we talked a bit about Earth, but last we talked all about Mars. But you work on so many different missions all over the solar system. Why is that kind of, seismic knowledge useful for these missions all over the solar system?
If you imagine, stuff re-enters the atmosphere and hits the ground occasionally, basically on any world which has an atmosphere and a solid surface. And even then, the gas giants still get hit by stuff all the time. So on Mars, with InSight, we know that we detected a number of impact events. And again, as we talked about earlier and previously, both the explosions in the atmosphere and the things striking the ground. InSight's now over, but moving forwards, we'll have a seismic mission that I'm part of the team for going to the moon called the Farside Seismic Sweep that will detect impacts. Of course, there's no atmosphere on the moon, but we know that we will see from Apollo times the sort of signatures of meteoroids striking the surface. And then I'm also working on a mission called Dragonfly, which will take a seismometer and some geophones to Titan. And Titan is like Earth, except it has a really thick atmosphere. And it's a very extended atmosphere compared to Earth as well. So it's also possible that we will see things burning up in the atmosphere on Titan, though probably less likely than on Mars, just because the atmosphere is very thick and we think the impact rate on the outer side of the solar system is a little bit lower. But all of these techniques are kind of cross-fertilizing, if you like. The reason that we thought to look at the space debris on Earth is because we've been looking at impact events on Mars and we had some idea of what we might be looking for. Similarly, the reason that we're thinking about how we can sort of apply some of this work to Titan is because we've been looking at Earth on exactly what the diversity of signatures of stuff exploding in the atmosphere from space might be. So it's helping us to inform work on other planets, and that in turn is helping us to learn and sort of understand the data we see, the seismic data from things occurring within the Earth's atmosphere as well.
That's useful too to have both of those sides. On the moon, where there's very little atmosphere at all for it to stop these objects from coming in, so you get them slamming straight into the ground. Then Titan on the other end with this very thick atmosphere. I bet it's very rare that objects ever actually strike the ground on Titan because of how thick that atmosphere is and the fact that probably everything burns up before it gets there.
That's the current thinking. And if you look at the surface of Titan, it has very few craters, or at least compared to, say, Europa or, things of a similar size in a similar-ish part of the solar system without an atmosphere. So that atmosphere acts as a really strong filter. Basically, only the biggest stuff gets to the surface.
Are there any other worlds that you would really like to see seismometers on?
I think Pluto would be really interesting. Obviously, that's decades and decades away, but we know that it has active geological processes. It may have, or at least at some point, have had liquid water beneath the surface. Of course, there are other icy worlds in the outer solar system, like Enceladus, that would be really interesting as well. But for what I'm kind of looking at the moment, you really need an atmosphere for it to work. So I think Titan and then Venus would be the next big one. And we know on Venus, again, there's that strong atmospheric filter, but also stuff must be entering the atmosphere if we kind of extrapolate impact rates from Earth, Mars, and the Moon out to the inner solar system.
That would help as well, trying to learn more about the volcanic state of things on Venus, because trying to peer down through that atmosphere is really hard. We've found some what we think might be potentially geologically active places on Venus using synthetic aperture radar data from a long, long time ago. But man, if we could cover that world in some seismometers, that would be some data.
And there are people working on proposals to both have seismometers in the atmosphere on Venus, so sort of on balloons. You've got, well, I should call them infrasound sensors, really, but also folks working on having landed seismometers that work at extremely high temperatures and pressures and can record ground motions. Because as you say, we know we have volcanoes on Venus, so therefore it's very likely there's other kinds of seismic activity associated with that as well.
Mm-hmm. Well, I'm really glad that as far as we know, no one got hit by this object coming down. And this was one more opportunity for us to perfect our understanding of how things hit the Earth and how to detect them. Because it's about whether or not people are safe, but also about the animals and about the science of retrieving these objects that have been in space for decades. It would be wonderful to get our hands on this.
Absolutely.
Well, thanks for coming on and telling us all about this, and good luck on your future seismic adventures on other worlds.
Thank you so much. It's been great to chat again.
As we've learned, Cosmos 482 was just one of many large human-made objects that have made dramatic returns to Earth. While its story is unique, it's not alone. From defunct satellites to entire space stations, humanity's ventures into orbit sometimes come back to remind us of their presence in really unexpected ways. Events like this aren't just historical footnotes. they're a powerful reminder of the risks and responsibilities of space exploration. The number of objects that are returning to Earth also marks a turning point in how we think about monitoring objects above us. To talk a bit more about the biggest and most memorable human-made objects that have fallen back to our planet, I'm joined now by Dr. Bruce Betts, our chief scientist, for this week's What's Up? Hey, Bruce.
Hello, Sarah. Good day to you.
Good day. So we've got this upcoming event. By the time we will have released this episode, Cosmos 482 will have fallen down to Earth, but we haven't seen it happen yet, recording this ahead of time. But since we're talking about things falling back down to Earth, human-made things falling back down to Earth, I wanted to ask you, what are some of the largest things that have ever fallen down to our planet that humans created and put in space?
The moon.
If you've seen Moonfall, maybe.
Yeah, I'm on the special features for that tremendous movie. So anyway, you start really big. You got the Mir space station, the Soviet and later Russian space station for quite a long time that came on down in around 2001. And you got the Skylab, a much smaller space station from the U.S. that was hoped to be reboosted by the shuttle, but shuttle delays and increased atmosphere had it coming down in Australia in 1979, or over the ocean in Australia. Previous random space fact, did you know that part of Skylab was displayed in the Miss Universe contest of that year, which was held in Australia? One of the most
They recovered a piece and brought it.
Yeah, non sequiturs of space stations, of burning up. Other space stations, Salyut 7, and back in the 80s, there's another Soviet space station, Chinese space station, Tiangong 1. You got boosters that are sometimes big. For example, the Long March 5B booster from the Chinese, that those go up and then get spit back, and they're often can be quite large. And, Apollo was fairly decent size when it came ripping back into the atmosphere as well, but it was designed, thankfully, to survive quite well.
I bet it's kind of terrifying seeing something as large as a space station just come out of orbit. I know one of these days we're going to have to deorbit the International Space Station, and I'm hoping morbidly that someone gets some really cool videos of that thing coming down.
Yeah. I'm guessing someone will. If nothing else, it'll be quite visible from space. But they will intend to put it down in the ocean, presumably, or over the ocean.
Yeah, I know they're headed for Point Nemo, which is, where they try to angle a lot of these things. Also, funnily enough, if you're a fan of Lovecraftian lore, it's a location in the ocean very close to where the books would say Cthulhu is. So we're trying to feed the monsters some space things.
Well, keep him happy-ish while he's down there.
Right. But I should point out, and this is something that I realized as I was looking into this story, that there's this larger Cosmos kind of Soviet program, but there was a moment in planetary society history where we created a solar sail that we wanted to launch on Cosmos 1, which was, also related to Russia, but these are two very different programs, right?
I mean, the Soviets, later Russians, have pretty straightforward naming systems. So at least they have had in the past, if they launch satellites in Earth orbit, or in this case, that didn't make it on its intended orbit to Venus, it gets named Space, Cosmos. If it goes to Venus, it's called the Venera. If it goes to Mars, it's called Mars. If it goes to Phobos, it's called Phobos. And then you add numbers to it. So they've had hundreds, if not thousands, of Cosmos spacecraft. We had one, Cosmos 1, that was Russian built and others funded through Planetary Society. And so that was Cosmos 1, which failed on a Russian launch as well.
R.I.P. Cosmos 1. Space is hard, okay? Sometimes it's difficult, but that is really interesting to know that's a great naming convention for things that, you don't have to name each and every spacecraft completely separately. You can just look at the name and know exactly where it went.
Yeah, I think they've tried to get more creative recently, but then spacecraft haven't worked anyway, in terms of planetary. So, yeah, it is, except you end up with Cosmos 482 and Cosmos 1523. And so, I mean, they're just all Cosmos, which is, our cosmos or space.
And we've definitely had that situation where we're talking about exoplanets and it's like TOI 270b, but then there's also TOI 380b, and all the naming conventions make them a little complicated for people who aren't super in the know.
Yeah, well, they've got a challenge that they've confirmed well over 5,000 exoplanets, so it's a little hard to give everyone of them a friendly name, but it does get confusing. Same with asteroids. They eventually get names, but they start out, if they're near the asteroids, with numbers. They all start out with numbers, letters and number combinations, because there are a lot of them being found these days.
Yeah, space is big. Well, what's our random space fact this week?
I have a speed of planets going around the sun kind of thought experiment. Of course, Neptune is out there, way out there. It's going really fast by human standards around the sun, but how fast is it going, say, compared to that little speedster Mercury? Well, on average, stay with me now, if you're Neptune and you've got the top rolled back and your Wayfarer's on, and you're cruising along at 100 kilometers per hour, 62 miles per hour, kind of freeway-ish speeds, then Mercury would have to be a commercial airliner going along at several hundred kilometers per hour.
Yikes.
Very similar to an Airbus or Boeing commercial aircraft.
Whoa.
Hey, Sarah, go out there, look up the night sky and think about planets. Thank you and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with more space science and exploration. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email, planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our dedicated members from all around the world. You can join us as we work together to build a brighter future for space exploration at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. And until next week, Ad Astra.